hi everybody. Today we have the honor of having Euhanna Ghadimi, who is a graduated PhD student of Automatic Control Department, which is now a division, by the way. So floor 6 of this building. He was working extensively on ADMM and optimization methods, optimizing hyperparameters of ADMM. And now he's working at R&D of Ericsson. So please.
Thank you so much. Thanks for inviting, and it feels really good to be back and be to the school and meet all of you. Yeah, so today's lecture is about ADMM, or alternating direction method of multipliers. So, and I understand this course is about learning, optimization and learning, and networks. So it's a nice combination of different areas that are naturally really related to each other. And ADMM is certainly one method that is applicable to at least more than one of these areas. And yeah, so here is the summary actually. At the end of this course, we will know about this, what is ADMM, which is practically a low complexity and robust method for a large variety of applications. And with ADMM is more to design some algorithm that is not really heavy in computation, and it's not, it's general enough, but it's perhaps not the best method if you want to consider a specific application. But it can be good for a big range of applications, and with relatively small effort of coding, you can get something that really works in many practical problems. So that's nice about it. And just a funny story, when I did my study, as Hussein said, I did a lot of work on this ADMM, because back then it was relatively new. So it's 2011 or 12 that it was a big hit, I guess, or reinvigorated or rediscovered. But then when I finished my study, I found also some practical application at work. So it was nice to see that it can be also applied to practice. So yeah, with that kind of story, we just start this method. And from the applications here, I said it has a lot of applications, right? Especially in this decentralized setting, when you have a number of agents or nodes or computers in the multiprocessing environment, or even in a totally disjoint fashion, that you have physically distributed computing resources or data for the learning, perhaps, that you cannot really contain them in the same central place. So this is naturally applicable to those conditions. And also, yeah, so for many non-convex problem also, there has been some development of this technique that can be applied to those techniques. But we don't, unfortunately, we don't review them today. But there are a lot of literature on that as well. So, yeah. And here is the outline. We will review some of the results of the previous lectures about the dual decomposition, and then we talk about the method of multipliers that is a predecessor of ADMM, or is like a parent of the ADMM. And then we talk about more specifically about ADMM and some hints and connections to other methods. We talk about the convergence results and how one can optimize hyperparameter optimization if someone is interested in those areas. And then we talk a little bit about application as well. Yeah. So let's go back to the classical methods that has been studied before for several decades, I would say. And that's a convex problem. If you have a convex problem of this form that you see, like f of x, and then we have some constraint perhaps, in practice you can formulate many constraints, like resource allocation constraints, if you have some resources that you want to allocate in a smart way, or you have some finance problems that you want to do optimization over assets, available assets. So all of them can be formulated in this way. And perhaps you have seen a lot of examples of this one. So just as a quick note that we will also cover cases that we have inequality. That might be a question here. But let's start from this simple case. But then we show how it will extend to those cases. The basic theory of the duality works that you formulate something called the Lagrangian, which is f of x plus y transpose ax minus b. So y is so-called the Lagrange multiplier, or yeah. So what it is basically a price. If you want to understand what it is, it's a price that you apply to a constraint violation. If you violate from the constraint, how much you are putting a price. In an economic setup, it has a very particular meaning. So intuitively, so we can formulate this problem, this function, which is called the Lagrangian. And one way to solve this entire problem is to apply so-called duality theory. So first, you formulate something so-called the dual function, which is basically an infimum of this Lagrangian with respect to the x variable. So what it means is you do your best. So imagine you are the guy who is you are the finance optimizer, or you are the guy who is responsible for resource allocation. You do your best to optimize your resources based on the given price. So the price is fixed, it's given to you, then you do your best to minimize your cost function. Basically, you replace the cost function with this affine term plus the cost function, and you minimize that. And that's called the dual function. And then there is another problem on top of that, like as an outer loop, that you apply maximization over that dual function. And that's called the dual problem. So again, the meaning is that now you go back to the job of this price setter or the dealer, the guy who tells you based on the current assignments of the resources or current state of your optimization decision with respect to x, this is the new price that you are setting. And you always try to maximize your price, maximize this function, sort of, yeah, with respect to the price vector. And then there are a lot of practicalities and assumptions behind. So basically, if everything shines and everything is fine, then you converge to something, if primal dual feasibility, and then you can recover a primal and dual solution. So let's not to get to the details there. Just, I think at this level it's good, so we can continue. Here is the first technique, the very rudimentary technique that is very old, that is applied to this duality, the Lagrangian method, and it's called the dual decomposition. Oh no, sorry, dual ascent. I'm jumping to the next slides. So in the dual ascent case, you do exactly the same procedure that I described, except that you specify how to do the maximization step for the dual. And that's done with a gradient step. So basically what is done is as the before. So you minimize the Lagrangian with respect to x. And then if you can just calculate the gradient with respect to the dual function, then you just see that that becomes really the constraint violation function, constraint violation term. And then you can try to maximize the dual problem, solve the dual problem, maximizing the dual function using a gradient ascent method. And then there is, as I said, there are theories about how to choose the step sizes and so on. And how it works in practice is really you go towards the as I said, the constraint violation. If it's surpassing this, or if it's like this value is positive or negative, you always have a change in your update. But as long as you don't move in terms of violation, if it's ax is at, when you calculate the xk plus 1, if it's equal to b, then there is no change in your y, so y value. So it converges, saturates, let's say, It's like a integrator, controller, if you are familiar with the control theory. Yeah, so we discussed about the convergence and this kind of stuff. So now the natural question comes after this dual ascent is how I can distribute this problem. How it's possible to solve it over a network. If I don't have the whole decision variable in one place, what happens? And that's the case here. So if you have a separable cost function, meaning that you have a x variable that is split into n pieces, and each can be kept in different computers or different nodes or agents, then at this level, this is trivially separable, right? Because everyone can does its job, and you are good because we have an x that is separable. What makes this problem interesting or non-trivial is when you have such kind of constraints, right? Because when you have constraints that are coupling to each other, for example, they have to, the summation of over resources, they have to satisfy a resource budget or something like that. Then you have to have some coordination between the solvers. So trying to do the dual ascent method with this setup, the first thing you do, you formulate your Lagrangian, right? And then when formulating the Lagrangian, you see that it's still it is separable with respect to the AI xi's, because what it does with this term of constraint violation is that you form a affine function, and affine function is separable by definition. So after this transformation of the Lagrangian, you still get a separable function. So it's really nice. So still you can do the minimization step with respect to the xi's now in a splitted way, and then you can do that in the distributed way in different nodes, as long as you know a global variable or price yk. And here is the really old method of this dual decomposition that is basically what I explained, plus that after you are done with your xi minimization in local nodes, then you have to do a gradient step, and that is over a global vector y. So it's like a master worker setup that the workers are calculating the xi's, and then they send their values to the master, and the master does this reduce operation, let's say. So averaging it and then distributing back the yk to all workers. So you see the message. Really, the message here is it works under certain conditions, but often very slow. Yeah. So the next section of this story is about a method that can accelerate or that can solve some of the issues that were existing with the classical dual decomposition methods. Or let's say classical dual ascent methods, because we are not talking about decomposition yet in this case of method of multipliers. What it is? What is the method of multiplier? So if we look at to the Lagrangian term, the old Lagrangian term, we recognize these first two terms, right? In the augmented Lagrangian, in the method of multipliers, we formed a special type of Lagrangian, and it's called augmented Lagrangian. We augmented with the penalty term, a quadratic penalty term. And exactly it is the same form of the residual that we had before. So we just add it as like a quadratic second squared norm in the simplest case, of course. Then, because there are other like spaces, and it can be more fancy than it, but let's discuss about only about the Euclidean distance. Then what we have here is something called the method of multipliers, the augmented Lagrangian, not yet method of multipliers. And if you want to go back and see that, okay, if I wanted to apply the same Lagrangian technique, then how I can transform my original problem so that I end up with the same effect. So it's the same as transforming your original problem with adding this additional cost to your. So it looks silly, right? Because of course, if you are satisfying your constraints, or there is no constraint violation, it just is 0. So you are not adding anything to your cost function. And of course, you don't care about this because it's just to make your algorithm to converge, because you are only interested in cases that x are equal to b. So from the designer point of view, it's a silly move, let's say. But it turns out that it has a very good properties for the convergence of your method, which is always hidden when you just apply the techniques. And in fact, it adds smoothness to your dual function. A lot of your dual function now has a Lipschitz constant. Then if you follow the convergence result, it says that it behaves, let's say. At the end of the day, it behaves very well, and you can control how it converges, and it brings smoothness and improvement in terms of convergence. But then, now, like, there is one tiny step still we have to take to get to this method of multipliers. And it's basically, very similar when you apply dual ascent, right, to the normal Lagrangian, except here you have the augmented Lagrangian term, and you have the same, like similar, let's say, similar gradient step, except that this step function, or step size, let's say, is particularly and carefully picked to be equal to rho. Rho is a scalar, is a constant penalty term. We will see in a minute the effects of it, how it will affect to the performance of the method, or the behavior of the method. So varying step size is replaced by fixed step size, and it happened to coincide with exactly the penalty term or constant. Now, if we look at to the, let's see, the optimality conditions for the method of multipliers, then we can see some nice things here. Okay, so this is one of the consequences that I was just mentioning. If you add this penalty term, then you get a more well-behaved dual function. And the effect of it is that now you can formulate more general classes of problems. Your function f, now it can take crazy values. It can be even unbounded from above, or it doesn't need it to be strictly convex, that previously you needed all of these restrictions to make your dual ascent method to work. Now you can formulate all of these things, and that's nice, because that's we will see in a minute that how we can use these things to formulate your constraint set in a generic form without caring about what they are. So, and then let's look at the optimality conditions of the problem 1. Problem 1 is the same problem that we were, I think it's this problem now, or the problem with augmented Lagrangian term. The first optimality condition is the primal residual, the primal feasibility, meaning that your constraint should be feasible at the optimality x star. The second one is if you take the gradient. Yes, of course, I assume that the f function is differentiable here. But similar things also applies to the case that f is not differentiable. So if you take the derivative of the augmented Lagrangian, then you get that and put the optimal values of x star and y star, this equation should be equal to 0, right? So if we want to develop this dual, it's called dual feasibility. For the case of the augmented Lagrangian method, we can do similarly here, right? So we take the derivative with respect to x of the so-called augmented Lagrangian, and let's put xk plus 1 and yk, so intermediate updates that we do. And let's study, let's see how it looks. So, and if you remember that f of rho was equal to f of x plus y transpose a x minus b plus rho over 2 squared. It's just taking the derivative. Then you get xk plus 1 plus a transpose, I should put yk here, exactly, yk plus, taking the derivative with respect to x, in this case, you get rho a transpose a xk plus 1 minus b, and that's it. So maybe we can factor out the a transpose. Then you get yk plus rho times a xk plus 1 minus b, which is quite nice because if you recall, this is just the y update, the Lagrange update case. So it's basically yk plus 1. And then you get plus 1 plus a transpose yk plus 1. And I put equal to 0, and it means that if you start from 0, it remains at 0, and it means that you can satisfy one of the so you get the dual feasibility for free, basically, the second term here, at each iteration. But with this careful setup of the step size of the Lagrange update to be equal to rho, you get that dual feasibility at each iteration, which is nice. So, and then it just remains to achieve the other one at the optimality or at the limit. So when it goes, when k goes to infinity, perhaps, if it if we haven't done any mistake, then this hopefully goes to 0 as well. We will see the results about the convergence and what are the conditions and so on. Yeah. So we already discussed that this method of multiplier improves the convergence properties of the dual ascent compared to the dual ascent, but there is a cost, of course. Always there is a cost to something good, and that's when the case that we want to have separable functions. Just because of adding this additional quadratic penalty, now no longer our Lagrangian or augmented Lagrangian is not separable because of that the quadratic penalty case, and that basically means that we can no longer do the x minimization the first step in parallel, because you have to optimize for all x's because of the complicating constraint in the quadratic case. And basically now it's really naturally comes ADMM. ADMM is just a natural trick to solve this issue. So the issue is that because of the particular setup, or augmented Lagrangian term is not separable anymore, and we want a method that can solve that issue. And that's called ADMM, or at least one way of solving it. Yeah, so this is just a quick summary of the ADMM method. ADMM method is really not something new. It goes back to 50s even. They say 70, but I guess there are works or hints that discovered in the past decade that this some methods in 50s already can be transformed, or they are equivalent with ADMM. Then why this became really famous is basically because of that thing, because ADMM is a natural way of splitting, but now you have the problems, right? In the past, maybe we didn't have that much big problems with a lot of constraint set and decentralized setting that you cannot really keep all the data in one place. So I think that's something to do with this fact that this availability of these kind of problems make this algorithm attractive. And yeah, so basically we talked about everything in this slide before. So let's look at what is ADMM. So the so-called alternating direction method of multipliers has this canonical form, meaning that if we have two functions that we are solving, minimizing f of x and g of z, subject to, again, some complicating constraint. In fact, I mean, you can set gz equal to 0, then you recover something like the previous case, but still you have some z parameter that we will see in a bit how it will kick into the picture and how it helps. Then, as usual, business as usual, we formulate or augmented Lagrangian, like the case of method of multipliers. So f plus g plus some price vector times the constraint violation plus the quadratic penalty, as usual, as before. And then here is the change or novelty, let's say, compared to the method of multipliers. ADMM is nothing more than doing Gauss-Seidel in order to compute the x and z variables, meaning that in the first step you fix y. In the previous case you fix y, but if you were about to solve the same problem with the method of multipliers, you have to solve with respect to x and z at the same time, right? You have to calculate the minimization step of augmented Lagrangian with respect to x and z, because we just extended our primal variables to x and z. But here in ADMM, instead, what it does, it freezes 1/2, or let's say z parameter, z vector, and calculates the minimizes only with respect to x. And the same step for z. For the next term, you fix x and y, and you minimize with respect to the augmented Lagrangian with respect to z. And at the end, you do the business as usual. You do the Lagrange updates. So yeah, I think now we are done with this course, let's say, because this is the ADMM, and then that was the basic message of definition with ADMM. Yeah.
Augmented is just because we are adding this quadratic penalty.
Very good. Yes. Yes. That's the augmented Lagrangian, let's say. The normal Lagrangian augmented with some quadratic penalty.
Understand why we can do here like in different ways for x and z, but in the normal primal, like a normal dual x and we cannot.
I mean, this is just building a machinery for that case. I mean, if you apply this technique, the basic theory of the augmented Lagrangian doesn't hold anymore, because that assumes that you update all the primal variables, minimize the augmented Lagrangian with respect to all of the primal variables, right? But if the first trick that comes to your mind, or one of the few first ones that comes to someone's mind, to how to distribute or how to split this problem, is to do something like a Gauss-Seidel, right? Or in fact, if we go back, you could do it here, as you said, for the normal case of augmented Lagrangian, but then perhaps you do it iteratively before doing this step. So you do a couple of steps for x, like x, z, and then you alternate, and for a few steps. And then by then, maybe hopefully you converge to something that is jointly optimal for x and z. And that exactly could be the augmented Lagrangian method. Instead, here you don't solve the x and z to the optimality. So you freeze one and you just do one step of Gauss-Seidel. So multiple steps of Gauss-Seidel here probably converges to the switch back to the augmented Lagrangian. Yeah, I think this is again goes back to your question. We can do it one more time with more details. So as I said, if you were about to jointly minimize over x and z, then you fall back to the original of the method of multipliers. Then it says, yeah, so it's basically the definition of this Gauss-Seidel iterations, that you fix one and then you optimize with respect to another. And here it goes back. And I mean, this is maybe trivial, but let's do it with a more close look at how it happens that you have now a separable Lagrangian that you can split the minimization. So if you have the n number of workers, let's say, which each of them has a piece of your xi's, now I entirely remove the g and z parameters. So, but we can understand how it extends, for example, for this summation case that you have ai, xi. So you split your constraint set to blocks of primal variable and the blocks of the constraint matrix A. As we know, until here, it was no problem because it's a fine function, so it's a normal Lagrangian with summation over the different pieces, so it is separable. And then the problem was really here, that we couldn't split. Now with this technique of the Gauss-Seidel algorithm, is at each subproblem or subsystem I, you are optimizing only over xi, and you keep all the other xj's fixed. So for you, it will be aj times, it's not also, you don't even get the xj's, you get aj times xj. So it's a vector, might be much smaller in size from the other vectors, and you can be treated as exactly like b, so it's a constant term for you. So that's why you can just split it, and yeah, so you can just do the minimization with respect to xi's. Is it okay? Yeah. Let's look at the optimality conditions for ADMM. Similar steps, but like similar compared to the augmented Lagrangian, but for the ADMM steps. Now we have three conditions basically, and it's because we have two set of variables. We have x and z plus the dual variable, so we have three conditions. The first one is the primal residual, primal feasibility, and these two are the dual feasibility, one with respect to f and x, and another one with respect to g and z. And it turns out if we repeat the same exercise now with respect to z, so one of the dual feasibility conditions will be satisfied for free. Not all of them, because we do two steps now. And yeah, so this is the similar with the previous one, but only one of them is satisfied at each iteration, and the other one will be satisfied at the optimality. So let's see what we are talking about here. Yeah, so that's this now is talking about maybe probably not really important, but some nice trick that usually you will see if you read the literature about ADMM, that usually it's sometimes nicer to have shorter equations. So you can do this, I don't know how to call it, compilation of the squares trick or something. So if basically if you do the transformation like this simple case, that if you replace 1 divided by rho times the yk, and you call it the new variable u, then you can shift it inside the quadratic term and avoid the affine term. And of course you get more terms, but this will be constant terms with respect to x and z. So you can condense your minimization, and it's start look like the proximal operation. We will see about it, something like that. And doing this trick, then you will have this some so-called scaled format of the iterations. Yeah. So at each step, you only have f or g, like the function, plus a quadratic term, but basically in a new constant variable, constant term, because here, like ax and bz are still kept the same, but you change the coordinates, so you change the constant term. So there will be no big effect in terms of the performance, but only the calculations.
What's the definition for u?
Sorry. U is this. This is the transformation. So you divide yk by rho. Rho is a scalar, right? Rho was your penalty parameter here, or step size as well at the same time.
So this is the like you introduce the variable.
It's a Lagrange. It's still a Lagrange variable, because this is exactly. And another consequence is you will drop, of course, this rho here, because if you replace 1 over rho of y, you will see that you have to have multiply by rho here to recover y here. So I mean, it's very simple if you do it by hand, but it looks somehow nicer. It's fine, or yeah. So yeah, let's talk about a little bit more about these small things around ADMM. Imagine now if I set A equal to identity, so the first matrix in the constraint set. Then formulating the scaled version of this augmented Lagrangian, you will immediately see that this is a constant term, right? So if we call it minus v, let's say, then you have this form, which is equal to the definition of the prox operator of f and rho. What it means is that minimize f with respect to x, but stay close to v as much as you can. So I don't know if you have talked about the prox operators before, but this is something nice both in terms of interpretation and also computation, because for many of the cost functions you have a closed form actually for solving this QP. So it's really nice. It's going to be very efficient to apply to practical problems in that sense. Let's give some examples now for the functions that now we can really, because of two things, because of method of multipliers and ADMM, we can introduce new set of cost functions that it wasn't possible for the dual ascent case. For example, one good example is the indicator function that you have it here as well. So indicator function is something like if you satisfy a constraint or a condition, for example, if your x is bigger than a b vector, then you have cost of 0. Otherwise, the cost is infinity, is really harsh. So you immediately can see that it can embed almost all of the constraints that we have, like in terms of these affine constraints. Ax smaller than b or equal to b or something. As long as you satisfy your constraint, the cost is 0, otherwise infinity. And this, as I said before, it wasn't possible to solve this kind of costs with the dual ascent. But now it is, thanks to the augmented Lagrangian term or the quadratic penalty term, now we can have this kind of functions. And just going back to this argument, if I calculate now the x updates for corresponding to this cost function, if I replace f with indicator function, then it is simply a projection. The prox operator will be a projection of a variable, like if the input variable is v here. It's unfortunate that I call them both v. Please don't get confused here. But if the variable here is x or something, then yeah. So basically, you do the projection with respect to b here. One famous example of this one is this ReLU. If you work with neural networks, for example, you have this activation function that projects over the positive orthant, and that's basically prox operator of indicator function that penalize if you are on the negative side. Yeah. So we can analyze those cases if you are interested with these functions. And then another example here is the L1 norm case, when you have a minimization problem of this form, that you have ax minus b, like the regression term, and then you have a penalty term of L1 norm. And applying this to the prox operator to this function now, like if we call it z here, and apply it over that, you get something called the soft thresholding. So it's still analytical formula, so you can put it, and what it does is just shrinks the input towards 0 gradually. So if it's yeah, so here A here will be lambda divided by rho in ADMM format. So it shrinks the input variable towards 0, but step by step. If it's larger than A, then it's minus A. Then otherwise, if it's smaller than minus A, then it adds plus A. So at the end, it will be concentrated around 0. That's nice, but there are more examples that you can calculate it analytically.